So this question is one where you have superheating. So at state 1, instead of being a saturated vapor, you have a superheated vapor. So other than that, the processes are kind of the same. I didn't write down at state 1. So what I'm doing, I find this is helpful. Like if we have enough information to just look stuff up in the table, I write that in here so I know that we can get it whenever we need it. So at state 1, it's a superheated vapor, but we have a temperature and a pressure so we can look stuff up in the table. I haven't written down the enthalpy yet, but what we're trying to find is the enthalpies at each one of those 4 states. Once we do that, we can answer basically any question they ask us. Okay, so let's write down so we have the enthalpy at state 2, the enthalpy at state 1 at 10 megapascals, 480 degrees Celsius. 480, so that's 3321.4. So H1 is 3321.4 times 10 to the third joules per kilogram. We can also, so we already have the one for 2. We can look up the one for 3. So go to the saturation. At state 3, it's a saturated liquid. So go to the saturated liquid for 6 kilopascals. That's 0.06 bar. And you get a value of 151.53. Times 10 to the third joules per kilogram. And then, so the last thing we need is H4. We have everything else. We know that this is a liquid, so we can treat it as incompressible. So we know that H4 minus H3 is equal to the specific volume times the pressure at 4 minus the pressure at 3. The pressure at 4 is the same as the pressure at 1. So P4 is equal to 10 megapascals. The specific volume, you can treat that as 0.001, or you can look it up in the saturation table. The specific volume what 1.006 times 10 to the minus third. So I'll write that as just 0.001 times the pressure at 4, 10 times 10 to the 6, minus the pressure at 3, which is 6 times 10 to the third. And so H4 is equal to H3, 151.53 times 10 to the third plus 0.001 times 10 times 10 to the 6 minus 6 times 10 to the third. And for that, I get 161.52 times 10 to the third. And now, so H4, 161.52 times 10 to the third. And now you can just answer everything that it asks you based on that. Anybody have any questions about the procedure for that? The only thing that was different was that at state 1, we had a superheated vapor, so you needed a pressure and a temperature. One thing they could do is give you the pressure at state 4 rather than the pressure at state 1, and you just have to remember that that's an isobaric steam, the steam generator is isobaric. Okay. The next thing I want to do is an example where we have inefficiencies in the system, where it's not isentropic in the turbine and the pump. Okay. So this is a case where we have irreversibilities. And so I'm going to redo a calculation. We've done this example. I don't remember how many days ago, but you can find it. But now we're going to have isentropic efficiencies to put into it, and we'll see how the values all change. So here is the question. Not there. Where's this thing? I was just looking at this. Okay, so here's the question that we had before. We did an example that said saturated vapor enters the turbine at 8 MPa. Saturated liquid exits the condenser at 0.08 megapascals. The net power output of this cycle is 100 megawatts. And we calculated the thermal efficiency, the back work rate, the rate of mass flow, the rate of heat entering the system at the boiler, and the rate of heat leaving the system at the condenser. Now we're going to calculate these again. Is that far enough? We're going to calculate this again, assuming that the isentropic efficiencies at the turbine and the pump are both 85%, 0.85. Okay, so let's think about what we expect to happen. I mean, a lot of this you can get by just assuming things get worse, you know. The efficiency, well, if you have irreversibilities, the efficiency has to go down. So we expect to get a lower value of that. And we'll compare all these to what we got before. The back work rate. So remember, what that's saying is how much of the energy that's produced at the turbine needs to be spent to operate the pump. So you would expect this to go up, and that's what we're going to see. In order to get that same net power output, if the efficiency is down, you have to crank more working fluid through the system, so this is going to go up. You would expect to have to add more heat at the boiler, so this is going to go up. And then if you think about the conservation of energy, we have the same net work. Q dot C and W dot have to equal QB, so this also has to go up. Okay, so that's what we're going to see. Any questions about that? Just understanding the basic way that putting inefficiencies in affects the performance. So here are the results that we got last time. So these are the previous results for an ideal cycle. We got an efficiency of 0.371, a back work rate of 8.31 times 10 to the minus third, a mass flow rate of 104.7 kilograms per second, a rate of heat entering at the boiler of 170 times 10 to the 6 watts, and a rate of heat leaving at the condenser of, nope, this was 270 and the other one was 170, so 170. Okay, so that's what we're going to compare to. So let's draw the cycle. Here's our state 1. Here's our state 2s, so that's the one if we have an ideal cycle. State 3, state 4s, and we're going to get values like this, where this is the true state 2, and this is the true state 4. From state 1 to state, well, let's first do it like this, where we assume this ideal cycle. We're going to calculate those enthalpies, and then we'll use the correction factors to come up with our new enthalpies at state 2 and state 4. So if we're assuming that this is ideal, then from 1 to 2 is an isentropic turbine. From 2 to 3 is an isobaric condenser. From 3 to 4 is an isentropic pump. And from 4 to 1 is an isobaric boiler. And we know that at state 1, it's a saturated vapor, and the pressure is 8 megapascals, which means we can look this up in a table, anything we want. So at 8 megapascals, we want to use the vapor value from the saturated water table. What do we want to get out of the table? What do we want to take out of the table in order to do this calculation? There's usually two things here that we want to get for state 1 out of the table. Definitely we want to get the enthalpy, but usually we also want to get the entropy, because we know that that entropy is the same as at state 2. And state 2 is a little complicated because we have a mixture. We always have to figure out the quality at state 2. Okay, so if it's not given, we're going to have to calculate that by knowing the entropy. Okay. So at 8 megapascals, that is 80 bar. We want the enthalpy for the vapor, 2758. So H1 is 2758 times 10 to the third. And then we also want to get the specific entropy at that state. And so for the saturated vapor, that is 3.20, 5.743. Times 10 to the third. At state 2, the condenser is isobaric, and we're told that coming out of the condenser, we have a liquid at a pressure of 0.008 megapascals. So P3 is 0.008 MPa, and that means that P2S is also 0.008 megapascals. So now we can look anything up as long as we know the quality. And we're going to get the quality from knowing that the specific entropy is 5.743 times 10 to the third. Okay, so at state 2s, 5.743, I'll leave the times 10 to the third off for now, is equal to x times the specific entropy at that pressure for the vapor, .008, so that's up here. Specific entropy for the vapor is 8.228. Plus 1 minus x times the specific entropy for the liquid, saturated liquid at that pressure. So that is 0.593. And so 5.743 minus 0.593 is equal to 8.228 minus 0.593 times x. And so the quality is 0.675. Now we're going to use that quality to calculate the enthalpy at state 2 for the ideal case. So this is 0.675 times the enthalpy at this pressure for the saturated vapor, $25.77 times 10 to the third, plus 1 minus this, which is, so 1 minus that is 0.325 times the specific enthalpy at that pressure for the liquid, 173.88. So H2S is 1796 times 10 to the third. Okay, 1796 times 10 to the third. At state 3, we have a saturated liquid, so we can just look this up directly in the table. And that is the value that we just got here, 173.88. And so the last thing we have to do is figure out the specific enthalpy at this idealized state 4. So at state 4, we have H4 minus H3 is equal to the specific volume times the pressure at state 4 minus the pressure at state 3. And this is for S. This is the ideal state 4. So the enthalpy at 4S is equal to 173.88 times 10 to the third plus 0.001 times the pressure at state 4S. Since that's isobaric, we know that this pressure is 8 megapascals. Minus the pressure at state 3, which was 0.008 megapascals. And so the enthalpy at that state, that idealized state 4, and I got 181.87 times 10 to the third. Okay, well, now that we have all these values for the ideal case, now we're going to use the correction to find the true enthalpies at those states. So now we're going to use the isentropic efficiencies. H2, the true H2, is equal to H1 plus the isentropic efficiency of the turbine times H2S minus H1. H1 is 2758. This efficiency is 0.85. H2S is 1796 times 10 to the third. And H1 is 2758 times 10 to the third. This should be H2. And so our value for H2 is 10 to the 6. H2S. Okay. I guess I just typed it in wrong. 2758. Okay, so we got 1940.3 times 10 to the third. So that's the true value of the enthalpy at state 2. And then for H4, that is equal to 1 over the efficiency for the pump times the ideal enthalpy at state 4 minus the enthalpy at state 3 plus the enthalpy at state 3. So we got 1 over 0.85 times 181.87 minus 173.88. And these should all be times 10 to the third. Plus 173.88 times 10 to the third. And you get 183.28 times 10 to the third. So now we can go through, we have all the enthalpies. First, we want to calculate the efficiency. And what we're expecting, remember, is to get an efficiency that's somewhat smaller than 0.371. The efficiency is equal to 1 minus the quantity H2 minus H3 divided by H1 minus H4. So that's 1 minus 1940.3. I'm going to leave off the times 10 to the thirds. Minus H3, which is 173.88. Divided by H1, 2758. minus H4, which is 183.28. And you get an efficiency of 0.314. Okay, so I mean that's the one that tells you how much total efficiency is decreased by those irreversibilities in the pump and the turbine. Then we want to calculate the back work rate. The back work rate is H4 minus H3 divided by H1 minus H2. In the ideal case, we got 8.31 times 10 to the minus third. Do we expect this to be lower or higher? Higher, yeah, because we're going to have to use more of our energy on the pump. And so we got 183.28 minus 173.88 divided by 2758 minus 1940.3. And we get a value of 0.011. Okay, so next, what do we want to calculate? The mass flow rate. We know that the net work, so W dot at the turbine minus W dot for the pump is equal to 100 times 10 to the 6. And we know that W dot for the turbine over M dot is equal to H1 minus H2. So that's 2758 minus 1940.3. This is times 10 to the, both of these are times 10 to the third. And so that is 817.7 times 10 to the third. And the work for the pump divided by the mass flow rate is 183.28 times 10 to the third minus 173.88 times 10 to the third. And so we get 9.4 times 10 to the third. And so WT over M dot, I guess we can write it like this. WT minus WP dot over M dot is 817.7 times 10 to the third minus 9.4 times 10 to the third over M dot. And that's equal to 100 times 10 to the 6. So M dot is equal to 817. Oh, because no, I'm sorry, I did that wrong. So we have this. And okay, algebra. Okay, so we have this is equal to 300. And so 808,300 is equal to 100 times 10 to the 6th times, that's the same.
No, 808,300 M dot is equal.
Times M dot, good Lord. Times M dot is equal, thank you, times 10 to the 6th. And so M dot is equal to 123.72, and that's kilograms per second. And we're comparing that to 104.7. So we expected that to get bigger, and it did. Okay, so now for the heat at the boiler. We know that Q dot at the boiler divided by M dot is H1 minus H4. And so Q dot at the boiler is equal to M dot times the quantity H1 minus H4. So that's 123.72 times 2758 times 10 to the third minus 183.28 times 10 to the third. And so that rate of heat entering the system at the boiler is 3.185 times 10 to the 8th. This is in watts. And that's compared to 270, 308 compared to 270. So in order to get the same amount of energy out of this cycle, you need to put that much more energy in at the boiler. And then the last one, how much energy is lost in the exhaust. Q dot at the condenser over M dot is H2 minus H3. So Q dot is equal to M dot times the quantity H2 minus H3. That's 123.72 times the quantity 1940.3 times 10 to the third minus H3 173.88 times 10 to the third. And you get the QC dot is 2.185 times 10 to the 8th. Well, actually, we could have just used the equation that says Q dot at the boiler is equal to Q C dot plus W dot. But so what we got when we put those inefficiencies in there is these results, the results of the arrows there. Any questions about that? Okay, that's all.
So class Monday, no class on Wednesday.
Oh, yes, that's right. So there's no class on Wednesday. There is school on Wednesday, but my classes are canceled on Wednesday. I'll put that on D2L. What?
Wednesday, Friday off next week.
Yes.
Wednesday and Friday next week?
Yeah, just for my classes Wednesday, and then Friday for the whole school. Hi.